All right, so in this video, we're going to look at improper integrals of the second type. If you've not watched the first part, you might want to consider going back and watching the first part of this series before you do this one. I will link to it in the description of this video. Okay, so our second type of improper integral is the type where there is a discontinuity, an infinite discontinuity, at either one of the endpoints or between our bounds of integration. So let's take a look at a situation here that I have. So if I want to calculate the antiderivative from a to b of f of x dx, the problem that I have is b is a vertical asymptote for my function. So I'm going to do something similar to what we did with the type 1 integrals, and that is if I stop my integration bound somewhere before b at t, then what I have is a finite area under the curve. What I have is a finite integral. And there's a finite area associated with that finite integral. As I allow t to approach b, right, each time I stop, then that gives me a finite bound. So what I want to know is what happens as t approaches b, just like in the last type when we let t approach infinity. So what I'm going to do here is the same idea. If b is my asymptote, I'm going to take the limit as t approaches b. Now, I have to be a little careful here because depending on where which endpoint is the asymptote, I'm approaching either from the left or from the right. So because my right-hand endpoint is the asymptote, t is approaching b from the left. And there are times when that might make a difference. And then I'm going to do the antiderivative from a to t of f of t dt, f of x dx, sorry, f of x dx. Okay, so we're going to follow the same basic procedure that we did in the first video. Right? The only difference this time is instead of our interval of integration extending infinitely in the vertical direction, all right, our interval is a finite interval, but the area is infinite. The region is infinite in the vertical direction near the asymptote. All right, so we're going to break our definition down into three types, just like we did with the last set. All right, so we're going to define improper integrals. Okay, hang on, that's totally not right. Integrals type 2. Type 2. All right, so now for this we need, again, for all of our integration, we deal with continuous functions. All right, so we'll start with our right-hand endpoint being the asymptote. So if f is continuous, on the interval from a to b, b is open, and is discontinuous at x equals b, then we can take the antiderivative from a to b of f of x dx as the limit as t goes to 0 the antiderivative from a to t, f of x dx. All right, now the continuity allows us to write that equation. All right, but it doesn't guarantee that the limit exists. So this is if the limit exists. All right, and just like before, if it exists, and it's fine, if it exists as a finite number, then that is the antiderivative, or the definite integral. If it doesn't exist, then the definite integral diverges. All right, so that's the first case. Label these. The second case is if the t approaches, now what am I writing here? B from the left. Right, sorry. So the second case is if the other endpoint, right, if f is continuous, this time open at A, closed at B, and is discontinuous at A, all right, then we can write the antiderivative from A to B of f of x dx is going to be the limit as t approaches A this time. And because it's approaching A from the right of the antiderivative from t to b f of x dx. Again, if the limit exists. All right, so there's our endpoint. Our endpoints definitions. All right, now if the discontinuity happens somewhere within the interval, all right, that is between A and B, you've got an asymptote. All right, so the third case is if f has a discontinuity at some value c, where c is between A and B. Strictly between A and B, sorry. Right, we've already taken care of the endpoints. I don't want to have cases. And both the antiderivative from A to C of f of x dx and the antiderivative from C to B f of x dx exist, so both of those have to exist, that is, be finite, then we can write the antiderivative from A to B of f of x dx as the antiderivative from A to C f of x dx plus the antiderivative from C to B of f of x dx. And again, just like in the last video, we need both of those to exist and be finite for this to work. All right, so let's take a look at an example. All right, so let's do the antiderivative from 2 to 5 of 1 over the square root of x minus 2 dx. All right, so one of the things we might want to do here is to look at a graph. All right, so if we take a look at the graph of this situation, so here is the equation 1 over the square root of x minus 2. The left-hand bound at 2 is an asymptote. The right-hand bound is finite. All right, so you need to recognize that what you have there is a right-hand bound that is infinite. Okay. All right, so with that in mind, all right, where am I going here? With that in mind, I guess I need to go back to the board, don't I? So with that in mind, we're going to be using the second part of the definition, right? When the left-hand bound is infinite. So this is going to be the limit as t approaches 2. Now, since it's the left-hand bound, we're approaching 2 from the right-hand side, from the right, of the antiderivative from 2 to, from t to 5. Right, that's my infinite side. From t to 5 of 1 over the square root of x minus 2 dx. All right, now 1 over the square root of x minus 2 is an elementary function, so it has an antiderivative, and its antiderivative is 2 times the square root of x minus 2. You would do that with a u substitution. All right, so we get here the limit as t goes to 2 from the right of 2 times the square root of x minus 2 evaluated from t to 5. All right, so this is going to be the limit as t goes to 2 from the right. So if I put in the 5, I've got 2 times the square root of 5 minus 2. So that's going to be 2 times the square root of 3 minus 2 times the square root of t minus 2. All right, and as t approaches 2, this approaches 0, right? So just as t approaches 2 from the right, the square root of t minus 2 approaches 0. So this whole thing equals 2 times the square root of 3. So this, yeah. Hang on. Yes, all right. So this, this one is finite, right? This antiderivative converges and has a finite area. It's a positive function, so we can interpret that as the area under the curve is finite. All right, let's take a look. Let's take a look at another one. All right, let's do the antiderivative from 0 to pi over 2 of secant of x dx. All right, now secant of x has an asymptote at pi over 2. You could graph it, or you could just look at your, the cosine is 0 at pi over 2. So secant is 1 over cosine, so if the cosine is 0, then the secant is undefined, or has an asymptote at pi over 2. All right, so we want to see if this converges or diverges, and if it converges, we want to get an antiderivative for it. All right, so since I know that my asymptote is my upper bound, it's going to be the limit as t approaches pi over 2. Now we have to think about this, right? If the upper bound is the asymptote, it's approaching from the left. All right, so this is going to be 0 to t secant x dx. secant x dx. All right, the antiderivative of secant is the natural log of secant x plus tangent x. So we get the limit as t approaches pi over 2 from the left of the natural log of the absolute value of secant of x plus tangent of x. And then we're going to evaluate that from 0 to t. All right, now at t, all right, let's see. So what are we going to get here? The limit as t goes to pi over 2 from the left. So if I put in t, I'm going to get ln of the absolute value of secant t plus tangent t minus ln of the absolute value of secant of 0 plus tangent of 0. All right, now the secant of, you know what, it doesn't matter, because the first term, as you let t approach pi over 2 from the left, the secant of t goes to positive infinity. The tangent of t also goes to positive infinity. All right, so this goes to positive infinity. This goes to positive infinity, which means the natural log goes to positive infinity. The second one is a constant, but it doesn't matter. All right, so this whole thing goes to infinity. So that means that the antiderivative from 0 to pi over 2 of secant x dx diverges. Okay. All right. Again, review your trigonometry if you need to, but you can graph this to get the basic structure of the function. That's fine. Or any part of it. All right. Let's take a look at an example of... All right, let's take a look at this one. From 0 to 3, dx over x minus 1. All right, so does this converge or diverge? And if it converges, what is the antiderivative? All right, now, the first thing you need to recognize here is that between these two values, we have an asymptote. All right, so this function is undefined, right? F of x equals 1 over x minus 1 is undefined. At x equals 1. And in fact, if you take a look at the graph, you've got a vertical asymptote at x equals 1, and the function looks like this on this side, and like that on that side. And we are going from 0, which is right here, to 3, which is right here. So between our two values, we have a point where the function is not defined. So that means we need to evaluate two antiderivatives. We have to evaluate the antiderivative from 0 to 1, and then we have to evaluate the antiderivative from 1 to 3. Yes, from 1 to 3. Now, I'm going to start with 0 to 1. All right, so I want to look at the antiderivative from 0 to 1 of dx over x minus 1. All right, so this is going to be the limit as t approaches 1. Now, since I'm going from 0 to 1, I'm approaching from the left of the antiderivative from 0 to t dx over x minus 1. All right, so the antiderivative and 1 over x minus 1 is an elementary function, so it has an antiderivative. The antiderivative is going to be ln of the absolute value of x minus 1, and then we're going to evaluate that from 0 to t. All right, so let's see. Okay, so if I put in t, all right, so if I put in t, I have ln of the absolute value of t minus 1 minus ln the absolute value of, put in 0, I get minus 1. And what I have now is, since this is absolute value, right? Since this is absolute value, as t approaches 1 from the left, let's see, as t approaches 1 from the left-hand side, I'm getting ln of 0 there. All right, so let's do this. Let me... okay, I know what I can do. Let's do this. All right, see, what I'm getting there then would be infinity minus infinity, and I don't want that because that's a L'Hopital's form that gets confusing. But if I consider that I have absolute value here, that second one is going to be 1. I mean, the absolute value of ln of negative 1 is, the absolute value of negative 1 is the same as the ln of, so that last term is going to be 0. So basically I have just the ln of t minus 1 in absolute value, which is the same as 1 minus t. All right, it doesn't really matter which way I do it, okay? 1 minus t is positive, though, so that means I can drop the absolute value sign, right? So 1 minus t is positive if we're approaching from the left. So that allows me to drop the absolute value sign. All right, now as we approach 1 from the left, this inside is approaching 0. I forgot my ln. This is approaching 0. Right? So as t approaches 1 from the left, 1 minus t approaches 0. So ln of 1 minus t approaches negative infinity. So this is negative infinity. All right, now because that part diverged, I don't need to do anything else. It doesn't matter what the other side does. Right? It doesn't matter even if the antiderivative from 1 to 3 were finite. The fact that this side diverges means the whole thing diverges. All right, so we can just take this at this point and say 0 to 3 dx over x minus 1 diverges. Okay. Now, you got to be careful with this here because if you hadn't noticed that there was an asymptote there and you just went ahead and tried to evaluate this without noticing that it was an improper integral, you would actually come up with a finite value. All right? In fact, if you take the antiderivative, right? We took the antiderivative of that without the bounds, we got ln of the absolute value of x minus 1. So if you were to just throw in the bounds without thinking about the fact that there's a discontinuity there, then you would get ln of 2 minus ln of 1, right? And that would be ln of 2, which is finite. All right, so you have to be careful. Actually, from this point forward, anytime you're doing a definite integral, you have to think about whether that definite integral is proper or improper. Right? So when you see a definite integral, you're going to want to look at the graph, and you're going to want to see if you have any discontinuities in your function. Okay? Okay, so I'm going to stop this video here and do the last part of this topic in the next video.